Hey everyone, let's jump right into this explainer and take a closer look at the invisible engine that silently runs basically everything in our modern world. From the second you grab your smartphone in the morning to the unseen networks managing our power grids and traffic lights, software is this invisible force shaping our entire day. But how often do we actually stop and think about how this intangible web is built? Well, today we're going to unpack the hard science and honestly the historical struggles behind creating the software we rely on every single day.
Real quick, here's our roadmap. We're hitting the invisible engine, the historical software crisis, busting software myths, the engineering solution, and wrapping up with the principles of building software. Let's get into it. Section 1. The invisible engine. What actually runs our world? Look, whether we're talking about a ridiculously complex air traffic control system keeping flights safe, or literally just the timer on your washing machine, software is essentially the boss. It's the invisible set of instructions telling the physical hardware exactly what to do. Without it, our most advanced hardware is basically just a very expensive paperweight.
Now, there's a really fascinating contrast here. Hardware, like a CPU or a motor, is physical, right? It's manufactured in a factory, and over time, it physically wears out. It rusts, it breaks. But software, it's completely intangible. It doesn't rust, and it doesn't physically degrade over time. But, and this is a huge but, it can absolutely still fail catastrophically because of hidden bugs, or just by becoming totally outdated as our needs change.
And because it's intangible, you can't just slap software on an assembly line and mass-produce identical parts. It has to be meticulously developed. We're talking very specific steps, starting with careful analysis of what's actually needed, laying out the structural design, doing the actual coding, and finally, relentless testing. This is exactly why the real cost of software is in that initial development phase, not in copying it later.
And you can see how this plays out across different environments. You've got embedded software running completely silently inside your smart TV or your car's braking system. Then there's real-time. Think air traffic control or hospital monitors. If those lag for even a fraction of a second, lives are literally on the line. And of course, business software, right? The banking apps and payroll systems we use daily. The stakes are wildly different depending on where that code lives.
Moving on to Section 2, the software crisis. Because, trust me, building these systems wasn't always a smooth ride. There was a time when this invisible engine almost completely broke down.
Back in the late 1960s, as computer systems started getting massive and incredibly complex, the industry slammed right into a brick wall. It was literally dubbed the software crisis. People were treating coding like some kind of dark art instead of a rigorous science. The results? Huge, expensive projects were collapsing under their own weight. Software was constantly delivered late, if it even finished at all. It was riddled with bugs, massively over budget, and completely lacked documentation, making it an absolute nightmare to maintain.
A lot of that code actually survived and became what we now call legacy software. Which naturally makes you wonder, if that old code from decades ago is so notoriously messy and risky, why on earth haven't businesses just replaced it all with modern systems?
Well, the reality is you can't just rip out the foundation of a skyscraper while thousands of people are still working inside it. These legacy systems are deeply wired into vital daily operations. Imagine trying to swap out a bank's core transaction database while millions of people are actively swiping their debit cards. It's wildly expensive and incredibly risky to touch them, so they become absolutely necessary to maintain.
Okay, Section 3, busting software myths. Because these dangerous misconceptions are exactly what caused that crisis to begin with, and they're why legacy code can be so messy today.
Let's start with a classic management myth. If the project is late, adding more programmers will fix it. Sounds completely logical, doesn't it? If a construction job is behind schedule, you just hire more bricklayers. But in software, doing this is literally like trying to put out a fire with gasoline. There's actually a hard rule for this called Brooks's Law. Throwing more people at a late project just multiplies the communication chaos. Think about it. The veteran developers have to stop coding to train the new folks, the communication channels get totally tangled up, and the entire project actually slows down even further.
Then you've got the customer myth. People think, hey, software is digital, so changing it is super easy and cheap. They figure since it's not a physical, concrete bridge, you can just pivot the whole foundation with a few keystrokes whenever you want.
Nope, not even close. If you start coding without crystal clear requirements or change them halfway through, you are going to face massive delays. It's exactly like changing the fundamental blueprint of a building while the walls are already going up. The rework becomes incredibly expensive and completely destabilizes everything you've built so far.
But listen,
Developers aren't innocent here either. They often fall for the myth that once the program is written, the job is done. They get the code to compile once on their specific laptop and just assume they've crossed the finish line.
The truth is, a working program is virtually useless if no one else can understand it or trust it to stay reliable. You cannot just bolt on quality as an afterthought. Good design, exhaustive testing, and crystal clear documentation have to be baked in from day one.
Section 4. The engineering solution. To save our digital infrastructure from these myths, the tech world had to totally pivot. We had to stop treating software creation as an art form and start treating it as a hard science. Enter software engineering. By applying strict scientific methods, the goals here become incredibly precise. Develop much better software, drastically reduce errors, save time and money in the long run, and actually make massive projects manageable. It's about bringing the exact same mathematical rigor to code that an engineer brings to building a suspension bridge.
Finally, Section 5, Principles of Building Software. How do engineers actually pull this off? Let's look at the foundational blueprints they use to keep everything from collapsing. First up is separation of concerns. Instead of building one giant tangled spaghetti monster of code, engineers break the system into separate independent chunks, like keeping the user interface, the part you actually click on, entirely separate from the massive database in the background. That way, if one thing breaks or needs updating, it doesn't take down the whole system with it.
Next is abstraction, which basically means focusing on what a system does rather than getting bogged down in how it does it. Think about driving your car. You don't need a PhD in thermodynamics to press the gas pedal. Software engineers build similar interfaces so different parts of a program can talk to each other without needing to know all the messy internal mechanics.
Then there's the famous KISS principle: keep it simple, stupid. In engineering, being overly complex isn't a flex. In fact, simplicity is the ultimate sophistication. A design approach that actively strips away complexity, dramatically reduces hidden errors, and makes the whole thing so much easier to maintain.
And lastly, stepwise refinement. This is how engineers tackle those massive, intimidating problems. You start with a very high-level, bird's-eye view of the system. Then you just gradually break it down, step by step, into smaller and simpler components until the problem is actually solvable. And it's these exact principles that stand between a fragile digital house of cards and a robust, reliable system. So the next time you open a banking app, check out at a store, or board a flight, take a second to think about that invisible, rigorously engineered infrastructure working quietly in the background. Because as software continues to evolve and run more and more of our world, we have to ask, are we building reliable bridges for the future, or are we just patching together the next crisis? Thanks for tuning into this explainer, and keep questioning the systems around you.